Hello, everyone, and welcome. Have you ever stopped to think about the science happening in your first cup of chai in the morning? Or maybe the salt you sprinkle in your soup? We're mixing things all the time, but why is it that some things seem to just vanish perfectly, while others, well, they just sink to the bottom? Today, we're going to dive into the really fascinating science of mixing.
Really think about it. When you make a simple oral rehydration solution, an ORS, or even just some nimbu pani, it's not like one sip is super salty and the next is just watery, right? Nope. Every single drop tastes exactly the same. And that simple, everyday observation, that's our first big clue to understanding a massive scientific idea.
And this right here shows us the two basic kinds of mixtures perfectly. On the one hand, you've got the lemonade. That's what we call a uniform mixture. Everything is blended together evenly. But on the other hand, you have this muddy water. That's a non-uniform mixture. You can clearly see the different parts because the sand just separates and settles right down at the bottom. See the difference? So, to really get to the bottom of why that lemonade mixes so perfectly, we've got to learn the lingo first. Let's break down the three key building blocks of what scientists call a solution. First up is the solute. So what is that? It's basically the stuff you're adding in. It's the sugar for your tea, the salt for your food, the flavor powder for your drink. It's the ingredient that's going to, well, disappear or dissolve into the other substance. Next, we've got the solvent. Now, this is the substance that's doing all the heavy lifting. It's the dissolver. And in most of our everyday examples, the king of all solvents is, of course, water. It's the liquid that the solute dissolves into. And what happens when you put them together? When a solute successfully dissolves in a solvent, you get a solution. That's it. That's the final product. That perfectly blended, uniform mixture we were just talking about. So solute plus solvent equals solution. Simple as that. Okay, now this is where things get really cool. This slide shows us what's happening at a microscopic level, a level you can't even see. The solute particles, those little yellow guys, they don't just sit in a clump. They spread out and get tucked in perfectly between the solvent particles, the blue ones. This super even distribution is the whole secret. It's the reason why every single sip tastes exactly the same. And here is a delicious example we all know and love. In the sugar syrup for gulab jamun, what we call chashni, there is a massive amount of sugar dissolved in a pretty small amount of water. Now, you might be thinking, wait a minute, there's way more sugar than water there. And by weight, you're right. But, and this is the key, water is still the one doing the dissolving. So water is still our solvent and the sugar is the solute. So this leads us to a great question, right? Can you just keep dissolving sugar in your chai forever? Is there a limit to how much stuff a solvent can actually handle? Let's find out. Just imagine this simple experiment with me. You take a glass of water, you add a spoonful of salt, you stir it, and poof, it disappears. You add another one, it dissolves too. But if you just keep on going, spoon after spoon, you're going to reach a point where the salt just sinks to the bottom, no matter how much you stir. The water is, for all intents and purposes, full. And this visualizes those two important states perfectly. A solution that can still dissolve more solute, like the clear one on the left, is called unsaturated. It's still got room. But once it can't dissolve anymore, and that extra stuff starts piling up at the bottom like on the right, it has become a saturated solution. It's reached its limit.
Now, this fullness limit has a proper scientific name, of course. It's called solubility. It's the absolute maximum amount of a solute that can dissolve in a solvent at a specific temperature. And trust me, that last part about the temperature is the key.
Because here's a neat little trick. If you have a saturated solution, how can you dissolve even more? Well, a lot of the time, you can just heat it up. For most solids, like sugar or salt, increasing the temperature actually increases their solubility. This is exactly why you can dissolve way more sugar in hot chai than you ever could in a glass of iced tea. Okay, so we know why some things dissolve. But what about the things that don't, like that sand we saw at the beginning? Why do they sink, while other things, like a piece of wood, float? The answer to all of these questions comes down to one single super powerful concept: density. Before we even get into any math, just think of it this way. On the left, we have a dense forest, lots of trees packed into a small area, right? On the right, a less dense forest, with all the trees spread out. That's really all density is. It's just about how tightly packed the stuff is in a certain amount of space. And here's the simple formula for it. Density equals mass divided by volume. Now, mass is just how much matter, or stuff, is in an object, and volume is how much space that object takes up. So density is literally a measure of stuff per space. So how do we actually measure this for an object like a stone? It's a really simple three-step process.
First, you find its mass using a scale. Second, you find its volume by seeing how much water it pushes aside, or displaces. And finally, you just divide that mass by the volume. That's it.
And here's what that looks like in practice. On the left, we get the mass from a scale. Easy enough. On the right, we measure a starting amount of water. Then we drop the stone in. You see how the water level rises? The amount it rises by is the exact volume of the stone. Then you just take the mass, divide it by that change in volume, and boom, you've got its density.
Now that you understand density, I promise you're going to start seeing it absolutely everywhere. This one simple principle explains so much about the world around us, from deep inside the earth to high up in the sky.
Let's take hot air balloons. Why do they rise? It's all about density. When you heat the air inside the balloon, all those little air particles spread out. The air becomes less packed together or less dense than the cooler, denser air around it. And what do less dense things do? They float up.
Or just think about a simple bamboo raft. For centuries, people have known that materials like bamboo float on water. Why? Because the bamboo itself is way less dense than the water it's sitting on. It's a perfect practical application of this fundamental rule of nature.
But here is probably the most incredible example of all. You see, almost every single substance on Earth gets denser when it freezes. It packs in tighter. But water is a total exception. As it freezes into ice, its molecules actually expand, making the ice less dense than the liquid water. This is why ice floats. And that floating layer of ice insulates the water below, allowing fish and other life to survive the cold winters. This one strange quirk of density is one of the key reasons life on our planet can even exist as it does. It's amazing.
So let's bring it all together. Let's do a quick recap. We've learned that a solution is a perfectly uniform mixture. We found out that solubility is the limit of how much you can dissolve, and that you can often change this limit with temperature. And finally, we discovered that density, that simple idea of stuff per space, is the powerful secret behind why things sink or float. And now, to finish up, a little challenge to test what you've learned. A fresh egg sinks in regular tap water because it's denser than the water. So, using what we've talked about today with solutions and density, what could you add to that water to change its density and make the egg float? The answer combines everything we've covered. Give it some thought. Thanks for joining us.